That's annoying. Okay. Okay. Is that stream working? Is that a good start? Just taking. Yeah, there it is. Oh yeah, I can see it. Yeah, all good. Cool. We'll be continuing off of the last lecture from I think it was Tuesday, Monday, and this will be doing the calculus part of 113 and 141. And I guess let's just make a start. First, a quick announcement: the MathSoc X Datastock presents Forbidden Games Camp. Bunch of yap there. Ticket release, location, time, all this is written here. I guess turn up. Cool. Sets, inequalities, and functions. Let's make a start. So this first question, it's solve the absolute value of 4x minus 5 is less than 3. So how do we tackle this? Well, firstly, it's obvious that if I didn't have these absolute values here, then I could very easily just evaluate this inequality here, and I could solve for x from here. And so I really want to think of ways where I can get rid of the absolute value signs. So let's think about how these work firstly. If I have the absolute value of a positive number, this just remains as is. And that works for any positive number, it doesn't matter if it's real, rational, whatever, it will always stay as is if it's positive. This is true for 0 as well, because you can argue 0 is neither positive nor negative, this will stay as 0. All of these will work fine. So I guess it would make sense for now if, let's just assume this inside bit. We're going to consider two cases firstly. We've got case 1 and case 2. For my case 1, I want to consider what if this inside bit, what if this inside bit is positive? Well, I know that if that was just positive, then my absolute value signs are redundant. They literally just do nothing here. So I can just get rid of them, and I can continue with 4x minus 5 less than 3. And I should consider let's do first, let's consider when this is true. So this is true if and only if my 4x minus 5 is greater than or equal to 0. Okay, well in that case, I know that 4x would be greater than or equal to 5, and x would be greater than or equal to 5 orders. Okay, that's fine. And then what do I know? What else do I know? Well, now I can try and solve this. So let's say 4x minus 5 is less than 3. Now I've finally done, let's just get rid of these absolute value signs. I'm only considering this, and I know if I'm only considering in this case, then this inside bit is positive. So I know that 4x is less than 8, and x is less than 2. So for this case, I know that my values for x, where this is satisfied, is 5/4 as my lower bound, all the way up to 2. Cool. Let's consider the other case that I didn't mention, where what if this inside bit, and I'll drag this over to the side for now, what if this inside bit was negative? Okay, let's think about how that works with absolute values. So if I have the absolute value of -1, this will obviously turn into 1. If I have the absolute value of, again, let's say negative pi, this will become pi. And notice in general, what happens is this inside bit goes from being some negative, and it gets multiplied by -1 in order to become a positive. And that applies for a variable as well. Let's say this is absolute value of x. If I know x is negative, if I know this for sure, then the absolute value of x would be negative x. Because I guess let's see a value. If x was -3, the absolute value of -3 would be 3, which is -1 times -3. So we're going to use that same principle here. Let's consider, what if my 4x minus 5 was negative, right? So I guess that would be equivalent to saying 4x less than 5, x less than 5/4. And now, how does this impact my absolute value sign? Well, I know that this is the same. If this is true, then I just multiply this by -1 to take it out of the absolute value sign. I'm applying just this thing here, where I have this entire thing, my 4x minus 5, all being negative. So negative of 4x minus 5 is less than 3. I know 4x minus 5 will be greater than -3. 4x is greater than 2, and my x is greater than 1/2. Cool. And so, oops, this 4 disappeared. And so from this, I know that my bounds for this are half less than x less than 5/4. Well, this is my case 2 sorted. And I had my case 1 from earlier. So let's see how I can use these both to get my final answer. So let's look at what they've done. So again, case 1, they're considering this inside bit to be greater than or equal to 0. This is when I can ignore my absolute value signs. And by solving this inequality really easily, I get 5/4 less than or equal to x less than 2. And I can do just the same thing for case 2, 4x minus 5 less than 0 less than 5/4, and get the exact same answer from evaluating my inside bit. X is greater than a half. And so the overall solution is going to be, I guess if I look back at this, both this is true or this is true. So my overall values for x, where it holds, is half. So I'm taking this lower bit, is less than x, is less than 2. And this goes all the way up to my upper bound here. And you can see the same thing they've written down here. Solution is anywhere between half and 2. All of these values will satisfy my original inequality. And I did this by considering each case where the inside is positive or negative. Is there any questions with that? We cool? Cool. Now I'm just gonna keep going on to limits now. So the limit we're doing here is epsilon-m definition of a limit at infinity. We say that if the limit of x tending to infinity for some function is L, then for every positive real number epsilon, there's a real number m where if it's greater than m, then this equality is satisfied. Let's see what that means with the diagram, because there's a lot of words here. If I have some function, and I'm going to do a really simple function, let's just do something like this. And I'm going to tell you the limit as x tends to infinity is whatever this value is right here. I don't know what this is, I've just drawn any arbitrary line here. So, what this is saying is that for some epsilon, where it's away from my function from L, so let's say epsilon is this, and say it's this, and it could be either side, so I'll draw it up and I'll draw it down. It is saying that for this region here, and I will shade this in completely, there's going to be some value for x, and so let's say my m is here. I have some value m here, such that as long as my x is greater than that, my function will always be within epsilon of my limit here, L. And this is going to be always true, but the important thing is we don't actually always have to find this very lowest number. It could even be somewhere here, right? Notice that in this case, anything above here, this is always, all of these values for x, they're also within my bounds for epsilon either side. It doesn't matter which way it is. So I can consider this either side, and this any m is true, as long as everything above it satisfies an inequality. The reason I specify this is because let's consider another case. And this one's a little bit more interesting. I'm going to consider this function here. And I'm going to tell you that the limit here is, let's say it's 0. And so anything within these bounds here, I won't shade this fully, you can get the idea. Anything within these bounds here will satisfy the inequality. So anything below here is within my bounds, and anything above here is also within my bounds. So which one am I really considering? Do I write this as m, or do I write this as m, or maybe something over here? Well, remember that my m is anything above it. So if I have m here, and I look at above this m, let's say somewhere around here, these x values is all the way up here. It's nowhere even close to being within my epsilon distance. This is my epsilon distance. It's nowhere even close to being within that. So I have to consider something that is further up here, and let's say around here. So this value m and above are the only ones I consider. Does that make sense? Cool. So how do I apply this? Let's look at this here. So the limit as x tends to infinity of x squared minus 2 on x squared plus 3 equals 1. Let's just plug it straight into this and try and show it. So I would have the absolute value of And what is my function? My function is x squared minus 2 on x squared plus 3. I know my limit here is 1, so I can do minus 1 is less than epsilon. Cool. So how can I evaluate this? Well, let's put this all as one fraction firstly. So I know this is x squared minus 2 minus x squared minus 3 all on x squared plus 3 is less than epsilon. Okay? And now how else can I rewrite this? Well, this x squared and x squared cancel, and I get minus 5 on x squared plus 3. All my absolute values still, all less than epsilon. Now, I'm going to apply some trick that we just did in the previous question. How can I get rid of these absolute values? Well, one thing I know that is this denominator here, this is actually always positive. Why? Because this any square number is going to be positive. If I add any positive number, this whole thing positive. So this whole fraction here will always be negative. It can never be positive. And so what can I do? Well, I know that to make it positive, I just get rid of this negative sign here. I know 5 is less than x squared plus 3, less than epsilon. Now, how can I simplify this? Well, recall earlier that I said we don't need to find this minimum m. I could even find some m that is higher up. So some m here would also satisfy the same inequality. And so I don't have to find this epsilon. It is for some epsilon that this has to be true. What that means is, if I take this fraction, if I make this fraction even bigger, and I still find an epsilon where it holds, then this entire inequality is still, this entire thing is still valid. And so how can I make this fraction bigger that will help me here? Well, if I make my denominator smaller, if I have my numerator on my denominator, if I make this denominator smaller, this whole thing increases. So I can do 5 on x squared is less than epsilon. I've made this value bigger, but I'm still showing there is some value of x where it's always under some epsilon. It doesn't have to be the same one, it's some epsilon, it's arbitrary. So here I can then rearrange, x squared will be greater than 5 on epsilon. Again, remember this square root could be positive or negative, but I'm only considering for positive because I want to go above. So x is greater than root 5 on epsilon. And we can see if I show the same working, exact same thing happens. Oh, yeah. No, sorry, it was this page. Yep, sorry. There we go. So exact same thing happens. They subtract L and they put it as one fraction, rewrite this in a simpler form, and then they show that it's x is greater than root 5 on epsilon. Then to finish up my working, one thing I would specify is, remember we said that there exists some m, so x greater than m. So just to finish up, I would also specify that my m here is root 5 on epsilon. This is the value that my x must be greater than, so that my function is always within epsilon distance from my original limit. Does this make sense with everyone? Cool. You can stop me anytime as well if I'm going too fast or something too quick. Next one, we are going on to more limit stuff. So here we're doing limit to some value x to 0. Well, I know that to evaluate this, let me read this first. Limit as x to 0 of 3x squared plus sine 2x squared all on x squared. Well, there's a couple properties of limits here that are worth noting. Firstly, if I have the limit, so let's go x to some alpha, I really don't care what. And this is the limit of two things added together. Something like this. Well, I know that if I have the sum of these two, this is the same thing as if I took the limit of each one individually. So this is limit of x tends to alpha of f of x plus the limit as x tends to alpha of g of x. I can apply both of these separately. And in fact, this is actually true for any of my operations. It is not exclusive to this one. And so if I had same with minus, or multiplied, the exact same thing applies here. Another really interesting one that will be used a little bit later is the limit, if I have x tends to alpha, of let's say f of g of x. So it is a composite function. Well, what can I do here? Well, let's assume that the limit of x tends to alpha of g of x only, this goes to some number L, right? We don't know what, let's just say it's some L. Well, I can reevaluate this, assuming f of L exists. So f of L has to exist, I'll say if f of L exists, then this limit, I can just chuck this little limit inside on the g of x where it actually applies. So this is the same as if I said that f of my limit of the inside of g of x, which I said goes to the f of L. This works just as well, and sometimes this is actually the only way to do it, as you'll see a little bit later, not right now. So let's go back to this. How do I evaluate this limit? Well, the first thing that I see is that I've got an x squared here, I've got an x squared here. This is going to be really easy to divide, so maybe it probably helps if I split up my fraction firstly. So, if I do limit of x tends to 0, and I'm going to split it exactly how I said earlier. So I know that 3x squared on x squared plus the limit of x tends to 0 of sine x squared on, sine 2x squared on x squared. Nothing funky here, I've just split up my fraction and I've applied the limit to each of them individually. Well, this one's pretty easy. This goes to the limit of x tends to 0 of 3. And what do I know about this? Well, there's no x here. And so because there's no x here, this actually doesn't change at all, right? Limit x tends to 0, but it doesn't care. There's no x here, it's not gonna change at all. So this whole bit, this just goes to 3. Nothing special there. All my x's are gone, it's just a constant value. Well, what about this other side? This other side is a little bit trickier, but it helps us to use something that we know already. One thing you might recall, and I think they listed there later, but I'll get to that, I'll show that in a second, a limit, if I'll say, let's say theta, going towards 0 of sine theta on theta equals 1. Try that better. This is a limit that will be really helpful to us, and we can apply it in lots of different ways. So let's see how I can use that here. Well, I see that it's kind of similar. I've got a 2x squared and x squared. It's not exactly the same thing. Biggest thing being there's a constant missing on the bottom here. So imagine if I could put a 2x squared here. Imagine if it was this. Well, this I can now evaluate because this looks just like this. So I know it goes towards 1. So how can I change this, what actually is, into something I can work with? Well, I just want to put a 2 down here. And how can I do that? Well, I'll just put a 2 up front. 2 times the limit of x goes towards 0 of sine 2x squared. And now I can divide by a 2x squared down here. This is something I can evaluate again. So the limit here, I can say that this is 3 plus 2 times 1, because I'm using this identity here. To be more precise, I should write that this isn't, no longer am I considering x tends to 0, I'm more considering 2x squared going towards 0. But effectively, if x goes to 0, then these two are the same thing. So I know that this will be 3 plus 2, which equals 5. This will be 2 times 1, which is 5. And you can see exact same thing happens here. They split the fraction firstly. This, they just go straight to 3. And they rewrite this in the form of this limit here. And this is the limit that we can just assume to be true. Are we cool with everyone? All right. On to continuous functions. A function is continuous at some point, x equals a, if the following 3 things are all satisfied. And all of these must be true, and this is really important. So a function is continuous at a point if f of a exists, so it has to have some value at that point. The limit as I go towards that point exists. And finally, these first 2 things are equal to one another. And this middle one is actually a little deceptive. There's actually 2 things that it really means. For a limit to exist, that really means that both the left hand, so I'd say x goes from, let's say, the negative side, a negative, of f of x, this value has to be the same thing as if I approached it from the positive side. And so what do I mean by that? So a good example I could show here, let's do something like this. I have an open circle here, and I have, let's do this, I have a point down here. Well, this is, clearly we can see this is this is not continuous, but why? So if I approach my function, this is my key point, let's call this alpha, for example. If I approach this point from my left-hand side, so I'm following this curve and I go all the way along to here, well, I get whatever this value is. Let's call this b. I get the value of b. That's cool. Well, what if I do from the other side? If I follow this all the way along, I go over to here, I get this same value b. Okay, well that works. Those two are the same. But what about the actual function value? Actual function value is all the way down here, and at this point here. This is my function value f of a. It is not equal to the limit. And because of this, I do not call this function continuous. I can consider another case as well. So what if I had a function that looked something like this? So I'll have something like this, an open dot, and it continues this way. Okay, well for this function, again, let's consider this point at x equals 0. Well, if I approach it from the left-hand side, then I get this value here. Okay, let's call this b again. I get this y value of b, that's fine. Well, what about the function value? The function value is also this point. You can see it's a solid circle. This is also b. So the right-hand limit and the function value are the same thing. But what about the left-hand limit? Left-hand limit comes down here, and it goes to an open circle. So this is, I don't know, let's call this point c. These two means that the limit as x tends to a of f of x does not exist. The left-hand and right-hand limits do not agree upon each other. They go to different points. Because they go to different points, I say the limit does not exist, hence this function not continuous. How can we apply this? Well, a really common case where this is applied is the intermediate value theorem. What it says is, let's say I have some point here, a comma f of a, and I have some point here, b comma f of b. Let's consider this interval between a and b. It's saying that for any y value between these two, so let's say z here, there must be at least one real number c in between my interval such that f of c equals z. So in between my a and b here, there is at least one value so that it equals this z value. Okay, well, let's actually see that in action. So here I can see that for this z value, there are 3 points where it equals the value I'm thinking about. And those are f of c1, f of c2, and f of c3. So let's write that f of c1 equals z, f of c2 equals z, and f of c3 equals z. There is multiple points here or multiple values for c where it is equal to z, the function value is equal to z, but the intermediate value theorem states that there is at least one. In this case, for this, you can see there's 3. If I chose, let's choose a new point. Let's choose this point here, and let's call this q. Well, for this, we can see there's literally only one point here, and we'll call this w. In this case, only one point exists, and that's f of w equals q. Is everyone with me so far? That theorem makes sense? Cool, cool, cool. And again, we're going to see a place where we can apply this. So, what is the maximal domain of a instead of r of this function here? I'm not going to read this out loud because there's a lot of stuff happening. So, one thing that's probably worth noting is when I talked about continuity, we know a lot of important things. And firstly, my elementary functions, so I write my elementary functions, and my elementary functions are things you've all seen before. So like maybe if I have a polynomial, x to the p, or if I have an exponential, or if I have a trig function, all of these are elementary functions. And all elementary functions, and any like match of them, are all continuous over their domain. So if I have some polynomial, I do x to the p, and then I add it to sine x, this new function is also continuous. Same thing if I did composite function. So if I had the sine of e to the x, this is also continuous. It is a composite of elementary functions. This is really useful, and we're going to actually use that in this question. So here I have this. What is the maximal domain of a instead of r of this function? Okay, well, let's consider this. For my cosine and my exponential, I can really plug in whatever I want. there's no restrictions there. It does just work for everything. So cos pi minus x, I could have any x, any pi minus x, all this works, all this works. The really interesting one that I have here that I can think about is this natural log function. For my natural log function, I know it can only ever take in values that are greater than 0 only. And because of that, let's just set up an inequality. I know the inside of all this, 2e to the x minus 1 on 2 plus cosine of pi minus x has to be greater than 0. Okay, well that's at least a step. How can I evaluate this? Well, first step, I think I can just multiply this denominator across, but it's an inequality, so I have to be concerned about flipping signs and things like that. So do I have to flip the sign here? Let's see. I know the cosine, and I guess I should say the only time I have to flip the sign is if this denominator was negative. So I'm really just trying to show that this denominator is either positive, negative. I want to figure out what it is. So I know the cosine of pi minus x is somewhere between -1 and 1. Don't know what exactly. I mean, obviously it changes for all my x values, but I know it's somewhere in that range. What about 2 plus that? Well, if I add 2 to all of those, I know this is somewhere between 1 and 3. So it doesn't actually matter what my x value is. I know this, I know my inequality here will always end up being positive. It'll all be somewhere between 1 and 3. Because it's somewhere between 1 and 3, I know I can multiply this denominator across without having to flip the sign, flip the inequality sign. So if I had, example, just to clear it up, if I had a over negative b, I know this is strictly negative, let's say b is positive, so negative b is definitely negative, and I had this inequality, then when I multiply it across, I know a is less than 0. But in this case, this denominator is positive, all good, I can just get rid of it. So when I multiply it across, 2e to the x minus 1 is greater than 0. Cool. And I guess this is really basic algebraic manipulation. Greater than 1, e to the x greater than a half, x is greater than ln half, x greater than negative ln2. Is there any questions with how I've found that domain bounds? Perfect. So that is my answer for this. So my set for A, I think they wrote it here. Set for A is anywhere between, so it's greater than negative ln2, and I can go all the way up to infinity because there's no bound here. Let's keep going. Cool. So considering intermediate value theorem, explain why f of c equals 1 for some c. So, yeah. So for this, I will look at my original function. I'm just going to move this to the side. Okay. I want to consider using intermediate value theorem, how can I show that f of c equals 1? So I'll say f of c equals 1. So let's look at my graph. And by look at my graph, I mean I'm going to make up some shape because I have absolutely no idea what this looks like. I'm not even going to try and guess. Let's say this is negative ln2. I know that it has to be greater than this. Function keeps going, no idea what it looks like. I've just drawn something. But I still know that this function is continuous. Why do I know it's continuous? Well, it's made up of just a bunch of elementary functions. So for my domain of A, remember it's only for its domain, it's domain of A, I know this function will be completely continuous. That's good to know. So that means intermediate value theorem can be applied here, because intermediate value theorem, if you remember, intermediate value theorem is continuous. Suppose that f is continuous. It must be continuous. Cool. So how can I apply this? Well, if I want to show that there is some value c that has a y value of 1, then all I need to show, I don't have to solve for c. The question just wants me to show that there exists some c. So I want to find a value such that it is lower than 1, and I want to find some value that is greater than 1. And in that case, I know there is some c between them where it works. Again, there is no special trick here. It is genuinely just trying some values. So maybe your gut goes to trying 0 first. And so let's see what that gets me. F of 0 equals, I've written it on the side. You can just plug it in. You can go to calculator, type it all out. I've got my answer on the side here. And then my f of 0 is 0. Okay, well, that is a good start. So I know that, I'll redraw this slightly, fix it up. I know it must look something like this. So my f of 0 passes through here. That's a good start. I'm going to show something that passes through 1. Okay, well, maybe let's try another number. Let's look at f of 0.5. Well, my f of 0.5 gets me 0.716. Not great. What that means is I know there is definitely a point here, and for my 0.5, I know there's definitely a point here. 0.716. Unfortunately, these two still don't tell me anything about my value c. So I will keep going. And maybe let's try f of 1. You definitely could solve this more algebraically and more rigorously, find some value where you definitely know it's greater than 1. It's just as well to just try these numbers here. Especially when you have a calculator, you can do it super quickly. F of 1 ends up getting you 1.112. So if I say this value here is 1, still in blue so it really stands out. This value here is 1. This goes all the way across to 1.112. So what does it tell us? Well, we know that by the intermediate value theorem, and let's see how they've written it, f of 0 equals 0, f of 1 is approximately 1.112. This is greater than 1. By our intermediate value theorem, we know that there must be some kind of c between 0 and 1, such that, let's see, in the interval, lies in the natural domain. I guess that's important too, because if this didn't lie within the domain for my a, then I couldn't consider this. But because of the intermediate value theorem, I know that between 0 and 1 is 0 to 1.112. There must be some kind of c somewhere between them, such that it is equal to 1. The function value is equal to 1. Again, I don't know what, I don't need to find what, it doesn't matter to me. But I just know by intermediate value theorem is continuous within the domain, hence there must be. That makes sense? Perfect. And on the same aspect, we're going to talk about differentiable functions. So, if a differentiable function as limit h tends to 0 of this, so this is just the definition of the first principle definition of the limit of a derivative, then the function is differentiable at that point. And importantly, if my function is differentiable at that point, it is also continuous at that same point. And that's really important because that's actually not true the other way around. I could have a function that is continuous at a point, but not necessarily differentiable. So if it's differentiable, it must be continuous, not vice versa. And again, really important to note that when I say this, if this limit exists, again, I'm really talking about if the left-hand side, so my left-hand limit of my stuff, I'm not going to write it all out, is equal to the right-hand limit of the same stuff. If this is not true, then the limit does not exist. So that is what it means for that limit to exist. And I'm actually going to use this right now. So, consider this function h real to real defined by this little piecewise here. Cool. Given that h is differentiable at x equals 1, we want to find values of a and b. Okay? So, let's consider the point at x equals 1. If I know it's differentiable at x equals 1, then the derivative, or the gradient, as I come from the left-hand and right-hand sides, must both be the same thing. So I'm going to make up some function. It's going to look like this, and then at x equals 1, maybe it goes like that. I've just made up, again, it should more be like, I don't know, something like this. Just made it up. But I guess it should more, so that. So, I want to consider the gradient as I come from this side and as I come from this side. Well, it's a little tricky now. There we go. Let's consider if I come from the right-hand side, so x greater than or equal to 1. How do I find the gradient of that? Well, I can just really easily derive this top bit. I get 2a, and I'm looking at specifically x equals 1. So it'd normally be 2ax plus 3, but I'm looking at x equals 1, so I'll say 2a of 1 plus 3. That is my gradient as I come from the right-hand side. In other words, that is this right-hand limit. And I know this is equal to the gradient. And so this is the left-hand, so this is from the left-hand side, my gradient of this function, which derivative of that is just 2. I know these two things have to be equal. And this helps me, this is a really simple equation, helps me solve for a. A equals -1, a equals -0.5. Does that make sense? So I've equated my left-hand and right-hand gradients because I know it's differentiable, so the gradient function exists at that point, and because both sides are equal, or because the thing is this, the limits of my gradient for both sides must be the same thing. Okay. I can move this off to the side. And let's continue with, so that's good. And what else do I know? Well, if this function is differentiable, remember I said it implies it's continuous. Well, what does it mean for it to be continuous? And as I said earlier, the limit as x tends to, we're going to talk about 1, so I'll write 1 here. Limit of x tends to 1 of h of x equals h of 1. And what does it mean for this limit to exist? Again, the left-hand side and the right-hand side must agree on each other. Okay, well, that's actually really helpful as well. If I know the left-hand side and the right-hand side agree on each other, let's do the exact same trick. Well, for this top one, as I approach 1, I know I can just sub that in. This is, I guess, the limit x goes to 1 positive of ax squared plus 3x equals the limit x goes to, from the 1 negative side, of 2x plus b. This, there's no issues here. I can just straight sub these in. So I get a plus 3 equals 2 plus b. Does that make sense? So I've equated left-hand side, right-hand side limits, and because I know it's continuous, these two are equal. And I will get b equals a plus 1. So b equals 0.5, because I found my a earlier. And just like that, I have my values for a and b. So I have my solution for a, it would be negative 0.5. I have equated my both sides of my limit, and because of that, I know that would be a plus 3 equals 2 plus b, and they get the exact same answers. A is negative 0.5, b is 0.5. Any questions with that question? Is that fine? Cool. Next, we are going to go on to mean value theorem. Mean value theorem is a really important one as well. So what does my mean value theorem state? I'll just read it for now, and then I'll draw a diagram to explain it. Suppose that my function f is continuous from a to b, this closed interval, and differentiable on my open interval of a to b. There exists some real number c in a and b such that f of b minus f of a on b minus a equals f dash c. That's a lot of, this is really confusing. So let's try and draw a picture to help us understand this. Okay, so let's draw this. I'm going to label some point, oh, let's get a curve here. There we go. Let's call that function f. It doesn't matter what it is. This point will be a comma f of a. And let's say, so this would be a. And let's say this point here would be b. And so this point is b comma f of b. Okay, well, what is this formula really telling us? So, let's look at this numerator. This is f of b minus f of a. That is the same as writing this distance here, f of b minus f of a. Cool. What about my denominator? Well, my denominator says b minus a. And so b minus a is equal to this. So what is this fraction really telling me? Well, this fraction is just finding the gradient of this line right here. So the line that connects these 2 points, that is what this side is telling me. So my f of b minus f of a on b minus a. It is just my literally just rise over rise. There is nothing fancy there, just very confusingly written. Rise on run of my 2 points. And what's it saying? It's equal to the gradient at some point c. And if c is between my 2 values here. So let's clean this up a little bit. Let's say I have some point c here. The c could be anywhere, I'm just drawing it. What this is telling me is the gradient of this line matches the gradient of the tangent at some point c. So let's, if I just take this and I move this, there we go. You can see the gradient of the tangent at around there. I try to draw it correctly, it's a bit off. This tangent equals the same gradient as that tangent. Or they're parallel lines, or however else you want to think about this. These two are parallel. Okay, well that's really helpful as well. Let's see how I can use that. Actually, firstly, is there any questions with how the mean value theorem works? This is a pretty important one. Yeah? Okay. So, So are there any issues with the stream? Are you able to check?
Seems good.
Seems good? Cool. Okay. So let's consider this. Assume that a differentiable function f exists. And it's important that's differentiable because I'm gonna, that's kind of actually. Sometimes there are some things that are like hints that I'm gonna have to need mean value theorem. I know that it has to be differentiable, maybe some inequalities sometimes, and these all are kind of telltale signs that I'm gonna use my mean value theorem. So assume that a differentiable function f on the real numbers such that the gradient of f of x is less than or equal to 1 for all x. Okay, that's interesting. Given that f of 2 is 2, also interesting, so I've gotten 1 point there, and it's asking me to show that f of x is greater than or equal to x for all less than or equal to 2. Okay, so what can I do with this? Well, firstly, hopefully maybe it's a little bit intuitive that there's some telltale signs that inequalities, the fact that it's differentiable, I might have to use mean value theorem here. And let's see how I can apply it. So I'm looking at x less than or equal to 2, so I'm going to consider that my x is somewhere lower, maybe equal to the number 2. Reason I'm going to say that is because I'm going to consider the interval from x, which is lower, to 2, where it's, as we have specified, x is less than or equal to 2. So that's my thing I'm considering. Let's chuck in the mean value theorem. So the mean value theorem, I apply it here. F of 2 minus f of x on 2 minus x is, so that's just straight mean value theorem, nothing special there, at some point x and 2. Is equal to the gradient at some point c. And this is the trick here for this question. I know that the gradient at all possible points, not even within this interval, just for all points, it is less than or equal to 1. So instead of saying it's f of dash c, what if I just say it's less than or equal to 1 for all of these points? Okay, well that's really helpful. And I can say this, and I can say this as well, because f dash x is less than or equal to 1 for all my real x's. Okay. This I can just easily bring across. Again, always keep in mind that do I need to flip this inequality sign or not? This x is less than 2. We specified it here and here. So I know that 2 minus x will always be positive. And that's something you should always keep in the back of your head when you're ever doing inequality stuff. So I can multiply across 2 minus f of x is less than or equal to 2 minus x. And you very easily write, therefore f of x is greater than or equal to x for this bound here. Because, and this is important, c is on the open interval. Remember, that is also how the mean value theorem states it. C is in the open interval between a and b. It can't be at a, it can't be at b, it's between them. So when I apply it here, I know that x has to be a subset between negative infinity and 2, right? Well, why is this important? What did the question actually ask? The question said x at x less than or equal to 2. In here, because of how the mean value theorem works, I've actually only said it's true for less than 2. I'm not including the 2 here. Okay, well that's a bit of a problem. I want to include the 2 as well. But this is really easy to fix. I know that f of 2 equals 2. And so because of that, I can just say greater than or equal to x for including 2 as well. So I proved it for everything in that bounds, and then I manually showed that at 2 it's satisfied as well. Does that make sense for everyone? So mean value theorem does an open interval, but I want to include the point 2 as well, and so I manually show it afterwards. Cool. L'Hopital's rule. L'Hopital's rule is definitely fun. What does L'Hopital's rule state? So I know that so let's do this, let's write this properly. So if this limit exists for two functions, a fraction, fx on g of x, then the limit as x tends to some a of the fraction of these two is equal to if I took the derivative of both sides on the top and the bottom separately. Well, why does this work? This is a little weird. This seems really counterintuitive. Like, how do you even get this? Well, let's look at an example here. Oh, one thing I should mention. This specifies, this is actually only true if we call it an indeterminate form. It only exists if this limit, if I just plug in, so I just find f of 0 on g of 0, if this is equal to 0 on 0, when I just plug them straight in, so it doesn't actually have to be 0, it could be f of a. if this is equal to 0 and 0, or if it goes to infinity, horrible infinity sign, if this goes to infinity on infinity, then this is what we consider as an indeterminate form. We have no idea where this limit goes for my original question. This is when L'Hopital's rule works. So let's look at a little case here. Let's say I've got some function and it's going to go like that. Okay? I'm going to call this f of x. Okay, and let's consider some other function. Let's do, maybe it's going something like this. Let's do something like here. And it's going to be my g of x. And I really want to hone in on this point right here. And I'm specifically looking at what if I have f of x on g of x. And I want to look at this point, let's call this a. So I want to look at as x tends towards a. Okay, well, I don't really know. Right here, like I said earlier, I can't plug this in. If I try and plug it in, I get 0 and 0. This is just not going to work, right? So what could I do instead? Well, like, what if I considered something kind of close to 0? Well, not close to a. So maybe, let's say I wanted to do, maybe not at this point, but what if I did this value divided by this value? Well, I could do that. That makes sense. But what if I got even closer? And what if I got even closer? So maybe instead of here and here, what if I did this little sliver there and this little sliver there? So I just drew those right there. What if I did that ratio? So I divided those two values. So it's like, maybe instead of a, I'm looking at a minus 0.1 or something. Well, if I wrote that, that would be the same as if I found the ratio between some small change in f of x over some small change in g of x. And you see how that works? I'm getting really small slivers right next to that point. And so I can consider this. If I divide both my top and bottom by by a small change in x, this is a really primitive way to just write the derivative at that point. This is some small change in the function. This is at, I should probably have written this limit again. Limit as this goes to some value. This is a really primitive way of just writing the derivative at that point. And so I could just write f dash a on g dash a. Do you guys see how that works? So if I have these things, obviously they have to go to 0. If they were going to some other point, then this whole thing just doesn't make sense, right? But if they're both going to 0, then I can consider those height values and just consider the ratios of those. Does that logic, that thought process make sense for how L'Hopital's rule works? Cool. So let me try and apply this. Let's consider this question. And the way we use L'Hopital's rule is not always obvious, and we're going to see a couple of examples through this whole seminar section, and L'Hopital's rule used in somewhat non-obvious ways. So, if I have L'Hopital's rule, the limit as h tends 0 of this fraction here, and that's what I just have to evaluate it. Okay, well, let's see how that works. Okay. So, if I just apply L'Hopital's rule, firstly, let's do a couple of things. Let's see, can I sub in my value? Well, if I can sub in my value, I don't even have to use L'Hopital's rule at all, right? Let's sub in the value, so I get e to the negative 1 on 0, I guess, on 0. Okay, well, subbing in didn't work. I'm dividing by a bunch of zeros. This is just a no-no. I can't do that. Well, what if I look at the limits now? So I look at the limit of this bit and the limit of this bit. Well, if this top bit goes towards 0, then I have e to the negative 1 on 0. This is going to go towards infinity, because my denominator gets really, really small. This fraction here gets really, really big. So it goes towards like e to the negative infinity. And this itself goes towards 0. Okay, so that's good. What about my denominator? So h here is just going to go towards 0. This is perfect, because this is my indeterminate form. I have a 0 on 0, could have had infinity on infinity, but this works too. And so here, L'Hopital's rule can be applied for this fraction. Cool. So I guess let's try it. And if I apply L'Hopital's rule, I will save us the hassle. And I know that this will go towards, what is it? Negative 2e to the negative 1 on h squared. All on h cubed. Okay. Well, this doesn't really look like it's helped me here. This e to the negative 1 on h squared, it's still there. This hasn't gone anywhere. And this h has actually gotten even uglier. It's now h cubed. And I've got even some more constant terms in front. This has just gotten a lot worse. So what can I do instead? Well, another neat little trick here that I guess is always good to have in mind when you're doing L'Hopital's rule is what if I change how this fraction works? So we can see here, instead, let's take my e to the, it's all laggy now, that's all right, e to the negative 1 on h squared on h. What if I divided both my top and bottom by the product of these? So what I mean by that is my numerator now becomes e to the negative 1 on h squared of h times e to the negative 1 on h squared divided by, let's make this line a little smaller, divided by h on h times e to the negative 1 on h squared. Okay, and the reason I'm doing this is because these will end up cancelling, these will end up cancelling, and I end up flipping my fraction in a sort of way. It's not the reciprocal, but it kind of acts like it. So my numerator has become h to the negative 1, and my denominator has become e to the 1 on h squared. Well, why have I done this? Well, this actually ends up being easier to do by L'Hopital's rule. But first, again, let's check. I can't just apply it. Let's check this. Can I do this with L'Hopital's rule? Well, my numerator, firstly, again, we'll do the same steps. Let me just sub it in purely. If I sub it in, I get 0 to the negative 1 on e to the 1 on 0. Exact same problems as earlier. I can't divide by 0. This is causing problems. It doesn't work by subbing it. Okay, well, let's look at limits then. If I look at the limits and see how this goes, the limit for this top bit, this limit will go toward, this is 1 on 0, and this top bit will go towards infinity, like I said earlier. So what about my bottom bit? E to the 1 on 0. This top bit goes towards, this is 1 on 0 again, like I said, goes towards infinity, and e to infinity goes towards infinity. Once again, I've got a nice little, this is infinity on infinity. Indeterminate form, I can use L'Hopital's rule. Perfect. So let's apply L'Hopital's rule to this new fraction here. And so when I apply it, I have the working here, so I don't have to rewrite it all by myself. I can apply it, I get these kind of fractions here. If I multiply h cubed on the top and the bottom, the reason I'm doing that is because you see I've got h squared and h cubed here. When I do that, I get this neat little fraction here. And this, if you look at how this tends towards 0 on infinity. So you can see this if you look at, again, you can't sub it in, but we can look at how it tends. This h just goes towards 0. This denominator is 2e to the 1 on 0. This goes towards infinity. This whole thing just goes towards infinity. And so, what does that mean? Well, if my numerator is getting really small, close to 0, and my denominator is getting really big, this whole thing is going to go way towards 0. Right? Top bit getting basically nothing. Bottom bit is getting really big. And so it's something really small divided by something really big. This goes towards 0. And so my original limit there will end up, this is the original limit, ends up going towards 0. Are there any questions with that? Does that make sense for everyone? Yeah? Cool. Perfect. Okay. Yeah. Let's consider the other part of this question. So the other part says, subsequently determine whether the function is differentiable at x equals 0. Well, what does that mean? I'll scroll down here. For it to be differentiable, the left-hand limit, the right-hand limit have to both agree, and it has to be equal to the function value. So I know the function value f of 0 equals 0. They did just give me that explicitly in the question, f of 0 equals 0. Cool. And let's consider now the limits. Well, I have limit x tends to 0, the negative side of 0, and this is e to the negative 1 on x squared. This is my function. This goes towards, yes, let's write it out, negative 1 on x squared. If this bit goes towards 0, this goes towards infinity, and this e to the negative infinity goes towards 0 itself, and 0 equals f of 0. And exact same thing, I won't bother explaining, exact same thing for the right-hand limit, nothing's really changed there. It's still going towards the same point, and it's still going towards 0. Cool. So I know that it is continuous, and this is my requirement for it to be differentiable, it has to be continuous. And now we're going to apply this rule. So for it to be differentiable, I know that f dash x has to equal this limit. Well, I've shown that the left-hand and right-hand limits are fine, so we know this works. And so f dash 0 equals the limit of f of 0 plus h minus f of 0, limit of h times 0, f of h minus 0 all on h. And we get this expression. Well, hopefully this is really familiar because this is the part we just ended up solving. And the part we just ended up solving was equal to 0. We did it all out, we did a lot of work just to get to the same thing. So this all equals 0. Hence, the function is differentiable at x equals 0. Does that make sense for everyone? Cool. Finally, or at least finally for my part, inverse functions. So inverse functions here. Yeah. Cool. Inverse functions, suppose that functions 1-to-1. Inverse of f will be a unique function of f. We normally note it with a little -1 in the power, where the range of f inverse is the domain of my original. So essentially all I'm doing is if I have some function, the inverse is just, it's finding the reverse. So if this x value equals this y value, then this, if I plug in this y value, oops, I'm going to switch colors. If I plug in this y value to my original function, I should get the same x value back. They do the reverse of each other. And obviously it has to be 1-to-1 in this case, because if I had this parabola or something, this isn't 1-to-1 and this no longer works, because for one specific y value, multiple x values arise. And of course, for a function, we know that for one input, there is only one output. So the main thing that we're covering here is the inverse function theorem. So what does it state? If f is 1-to-1 has an inverse function, and let's say it's g, then I have all of these points. G is differentiable. Derivative of g is given by this formula, right? And this formula is fairly easy to show. If I show something like y equals f of x, then I know that dy on dx equals f dash x. Similarly, if I have the inverse function, so my inverse function will be x equals g of y, dx on dy, x on dy equal g dash y. So I think I've written these with different letters. The question, I'll flip these, sorry. Hopefully I'm still following. So y is g of x, dy on dx is g dash x, s equals f of y, dx on dy is f dash y. So I know that dy on dx equals, and this is what I'm trying to find, so this is my thing, dy on dx equals 1 on f dash y, oops, f dash y, and I can just sub this in again. So I know my dy on dx is 1 on f dash g of x. And that is exactly what they've written here. So the derivative of that is 1 over the derivative of my inverse. Does that make sense? Are we have fun with that? Okay. And then this is a pretty simple one, but it's just applying this, and we'll see a question for that shortly. So, this is an alternate form that they have here. Basically, just have inverse, and the inverse, like I said, typically denoted by just power of -1 in the power. Exact same formula as earlier, they've just written it like this. It's whatever you prefer, really. So, question 9 here, what do we have? So consider this function from these bounds. F of x equals this. Find all critical points of f and determine their nature. What is a critical point? Critical point is one of three things. It is either it has a gradient of 0, it is undefined, or it is the end point of our range. A certain point of whatever. These are the three things it must satisfy in order to be a critical point. Or it has to be one of these three things. And so let's see what we can do. So we have our original function. I can tell you now this is an elementary function, right? And like I said, elementary functions are going to be continuous. We're not going to have to worry about it being undefined at all. So we're just going to look at these other ones. So I can take my derivative of f of x. I think it's fairly self-explanatory. and setting f dash x equal to 0 finds turning points. So I have this function equals 0, and this is my derivative. I rearrange, and I can just solve this. Sine x squared equals 1, and these are just finding solutions for x squared. Notice, or remember, this is my domain, so I'm only finding x solutions within this domain. And for this, you'll see you get pi on 2 and 5 pi on 2. Of course, if you just think about your unit circle here, there are going to be a lot more solutions because I can just keep going, right? Keep going around and around. Only these ones will have solutions within my bounds. And so I can solve for x and I get root 2 pi on 2, root 10 pi on 2. Both are points of inflection. You can check this with your calculator. Other critical point is the endpoint, which is the other one I said, and find that this is the global maximum. Are we happy with this? This is kind of long. Does that make sense? So that's part A done. That one's fairly simple. Explain why f is invertible. Say the domain of the inverse and find inverse of 5 pi on 2. Okay, well, for f to be invertible, what do we say? So f has to be 1 to 1. That's an important one, right? And how do we know it's 1 to 1? Well, there's a couple of ways that I know for sure, but an interesting one is this. Let's say, consider this. Earlier, I mentioned the parabola and how this isn't going to be 1 to 1. But what if my function was always decreasing or always increasing? In that case, if it's always decreasing or always increasing, then let's say something like this, it will never go back up, and I can never have two y values for my same point, right? Also, it's different points. So it's always going to be like this. And that's the same for if I have some function increasing. I know the same thing. There's always going to be one x value for each one y value. Well, that's going to be really helpful. And let's see how we can use that. Instead of finding an inverse, one way you could totally do is you could manually find an inverse. That's just not going to happen with this one. There's no way you can manually find an algebraic inverse for something like this. But we still can show that it has an inverse. It is invertible. And let's see what they do here. Oh, sorry. For solution A, they do also mention the calculator. Because I mentioned you can do it with your calculator. These are the maple syntax for ways you can do with student calculus. You can see critical points. You have your function, and then critical points. You can find it out. And this is some calculus stuff. This is just maple syntax, and it's included there just so you know. Sorry. Let's continue with part B. So part B, the derivative here, and I already found that from earlier. Well, I want to show that this, I can actually show it's always going to be greater than or equal to 0. How can I do that? Well, I know sine x squared is less than or equal to 1. And so for, remember, I'm considering, where was it? Positive values, right? And positive values are important because I know sine x squared is less than or equal to 1, if I multiply this side by 2x, multiply this side by 2x, I end up getting 2x is greater than 2x sine x squared. Hopefully that makes sense as well. I've nothing special there to multiply each side by 2x. My derivative ends up being 2x minus 2x sine x squared. And this will be greater than or equal to 0. Why? Because this is bigger than this. This is bigger than this. Does that make sense? Yeah? Cool. And so I've shown that this function will either be it's always going to go up or has a gradient of 0. And what that means is f is increasing in its domain, and it's 1 to 1, or injective is the other name, you'll see. And we also know it's continuous. I didn't actually say I meant continuity at the start, but again, this is an elementary function, composite of elementary functions. It's going to be continuous within this domain. So that's fine. Okay. So what was that here? So it is increasing 1 to 1, and it is continuous. As, like I said, it is a composition of continuous functions. Therefore, f is invertible. So the range is 1 to 4 pi plus 1, and this is my original function, the range. Again, you can find this with your calculator, or Maple, or whatever. And so the domain of my inverse will be the range of my original function. Does that make sense? Then for the last part, it said that find the inverse of 5 pi on 2. So, inverse of 5 pi on 2, this is a little tricky. And they've chosen 5 pi on 2 really intentionally. So, find the inverse of 5 pi on 2. In other words, for this function, I want to figure out what can I plug in so that this... hopefully this will load again. If not, I will rewrite it myself. Okay. It's saying, what can I plug in for my x value such that this equals 5 pi on 2? Well, they've chosen 5 pi on 2 really intentionally. And this one is not necessarily something you would have intuitively, something you have to think about for a bit. Cos, oh, there's liking me writing on that. Cos 5 pi on 2 equals 0. This one's fairly simple to prove. You can just look at this. It goes here, and this is 0 for my cos 5 pi on 2. And you'll notice that if my x squared equals 5 pi on 2, then for this function bit here, this would go to 0, and this would just be 5 pi on 2. And 5 pi on 2 plus 0 equals 5 pi on 2. So this question, because it was from the 114 exam, this was a really tricky one, because you had to notice that this was true, and so you had to identify that x squared here would be 5 pi on 2. And so I think I mentioned that here. Very tricky, this one. They say this, hence, if I know that, they should have written it here properly. If I know my x squared is 5 pi on 2, then that implies that my x would be root 5 pi on 2. Does that make sense, everyone? So my inverse of 5 pi on 2 would be root 5 pi on 2. That makes sense? This one was a little tricky, though. Like, realizing this little bit here, so you can sub that back in. Hopefully that makes sense. And now the final part. Where is this inverse differentiable? Okay, so let's consider my inverse function theorem. This is the derivative of my inverse, and I'm thinking, when can I say that when is it defined? Well, it's going to be defined for a lot of points. You can see here, I don't see why it wouldn't be defined. When wouldn't it be defined? Well, it's not going to be defined if this denominator equals 0, right? Because obviously I can't divide by 0, it's undefined. So that's actually that's a really helpful one to consider. So I go back down. When is this denominator equal to 0? Well, it'll be equal to 0 when the f dash, and I'll say the f dash of stuff, right? I don't really care what's in there. When the f dash of stuff equals 0. Okay, well that's my original function, right? When does the derivative of my original function equal 0? Well, hopefully you remember from all the way back in part A, we actually did that already. We found when the derivative equals 0. And the values we found were this x is root 2 pi on 2 and x is root 10 pi on 2. Those were the values where we have the inverse, or we have this derivative equal to 0. And so by my inverse function theorem, so I go back down, if I have 1 on 0, then it's not defined. And so for everything else, we can say it is defined. So they say the exact same thing here. So derivative is not defined when this bottom bit equals 0. This is true when this equals pi on 2 or 5 pi on 2. Hopefully you remember we had this thing here. We had pi on 2 and 5 pi on 2. And so we know our x values from that very first part. I don't have to repeat it. We have very first part, root pi on 2 and root 5 pi on 2. These are the values where this fraction is 1 on 0. And so for anything not in this domain, well, anything that isn't this, then we know it is defined. Does that make sense? Cool. I believe that is the end of my part. I'll let Yanu take over. There we go. How does this work? Still put this in. Right. Ah.
You guys can hear me fine? Okay, so now we're going to look at curve sketching, and particularly we're going to be looking at oblique asymptotes. So far, what you guys are probably familiar with are vertical asymptotes that probably look like this, and horizontal asymptotes. But what if we have an asymptote such that it was like a diagonal line, essentially, in the form y equals ax plus b. So that's what we're going to be looking at. So we say that a straight line given by the equation y equals ax plus b is an oblique asymptote for a function f if the limit as x becomes really, really big, f of x minus ax plus b equals 0. So what does this mean? Well, we can think of f of x as our function, right? And ax plus b as our line. F of x minus ax plus b. We can kind of think of this as the difference or the distance between f of x and our line. So if I were to draw an example real quick. So imagine this right here is our ax plus b line, and our f of x looked something like this. So this is f of x. Okay, so I see that as x goes really, really big, the distance between f of x and x plus b becomes really, really small. So I can say that f of x, well, basically approaches ax plus b as x becomes really, really big. In that way, I can say ax plus b is an oblique asymptote because f of x approaches it. So how can we use this? Well, we can use it if we want to sketch some interesting looking graphs like x squared plus 2 over x minus 2. So if I want to sketch this right here, there's a few easy steps or self-explanatory steps we can take. So one really easy step is to find the intercepts. So easy one, if I want to find the y-intercept, I know that I have to let x equal 0 because, well, that's when the graph crosses the y-axis. So when x is equal to 0, we get y is equal to 0 squared plus 2 over 0 minus 2, which is 2 over minus 2, which is minus 1. So we have a y-intercept of minus 1. And if we want to find an x-intercept, we can just let y is equal to 0. So we get 0 is equal to x squared plus 2 over x minus 2. Multiplying both sides by x minus 2, we get x squared plus 2 equals 0. X squared is equal to minus 2. However, since x squared is going to be always positive for our real numbers, real x, we can't have x squared be equal to minus 2, so there's no x-intercepts here. Now after that, next thing we can find is we can find our asymptotes. So the vertical asymptote is pretty easy. The way we find it is we just see where the denominator is going to be equal to 0. So if my denominator is x minus 2, when it's equal to 0, x is going to be equal to 2. So I see that, okay, x equals 2 is our vertical asymptote. Now to find our other asymptote, what we do is we see, okay, how does the function behave as x becomes really, really big? Essentially, what I want to do is I want to find, as x approaches infinity, what does x squared plus 2 over x minus 2 tend to? So the way we can do that is, see. So this is the limit as x approaches infinity. One way we can do this is we can use polynomial long division to find what x squared plus 2 over x minus 2 becomes, which you guys probably learnt. But another way, what we can do is we can turn the numerator into factors of the denominator. And what do I mean by that? Okay, so that means I want to have x minus 2, x minus 2, something like that, such that I can divide the numerator by x minus 2. So the denominator just cancels out entirely. So I want to do that right here. I'll show you what I mean. So I have x squared as my first term. That means I can factor it as x times x. But I want it in terms of x minus 2. So I can do x times x minus 2. But this gives x squared minus 2x, right? But we don't actually have any 2x on our original numerator. So we have to counter it by adding 2x again. So this is what we have so far. This is equal to x times x minus 2. I'm going to do the exact same thing for 2x. I know I can do plus 2 times x. Now I want it in factors of x minus 2 again. So I'm going to multiply by x minus 2. However, this gives 2x minus 4. But I know that in my original equation, I had plus 2. So if I want to go from minus 4 to plus 2, I have to add 6, because minus 4 plus 6 is 2. And now the denominator stays the same. Now if you notice, what I've done is I've turned the numerator into factors of x minus 2, such that I can just cancel it like that. So in the end, we have x remaining plus 2 plus. The 6 has no factors, so it just stays as 6 over x minus 2. Now this is what we get. If I want to see what happens as x becomes really, really big, our term on the right here, I see that, okay, x is on the denominator. So 6 divided by a really, really big number is just going to become really, really small. As such, what we have left is just x plus 2. And this is our oblique asymptote. Now we have our intercept and asymptote. We can start to sketch roughly what the graph's going to look like. So I said the y-intercept was -1, so I'll just plop that there. And the vertical asymptote was x is equal to 2. However, we also just found that from subbing x as a really, really big number, we get x plus 2 as our oblique asymptote. So x plus 2 looks something like this. I'll get rid of this. So I can kind of see that it's going to look like this here. Now, if I want to find the exact points, I can maybe use calculus and find the turning points. But using this key steps here, we can see that, okay, we know roughly what the graph's going to look like. So if I were to recap, so we found the intersections with the axes. So when x is 0, y is -1. We found the vertical asymptote. So this occurs when the denominator equals 0. So x minus 2 equals 0. So x is equal to 2. We found the oblique asymptote by changing it into factors of x minus 2, such that when we take x approaches infinity, the oblique asymptote, or what we just have remaining, is x plus 2. And then we know roughly how the graph looks. Do you have any questions? All right. So far we've been working with x and y in our Cartesian plane. However, there's another form we can use. It's called polar coordinates. So imagine I have a point, let's just call it P, relative to some origin. I actually can figure out where P is if I just figure out how far away it is from the origin, depicted by R, and what its angle is from the horizontal. That way, for example, let's imagine I have here, if R was 1 and theta was, let's just say 45 degrees, I know our point is going to be somewhere here, where this is 1 and this is 45 degrees. However, if R was, say, 2 and theta is, let's just say 30 degrees, I know it's going to be twice as long, but this is going to be 30 degrees. So can you guys see how we can map points using how far away it is and the angle from the horizontal? But what if I want to turn this back into x and y, right? Because we're on a Cartesian plane. I want it in terms of x and y. Well, what we can do is I can create a right angle triangle like this. So let's imagine I just label this x and y. I know that I have my triangle here. We know that from Patoa that the cos of theta is just going to be the adjacent, which is x, divided by the hypotenuse, which is r. So x is going to be r cos theta. Similarly, sine theta is going to be the opposite, which is y over r. So y is going to be r sine theta. As such, the Cartesian coordinates can be defined as r cos theta for x and r sine theta for y. Is that all good? All right, now let's see how we can use this. So we're asked to find the gradient dy of dx of r is equal to 6 sine 2 theta when theta is equal to pi on 6. Okay, so see that we have to find dy and dx, but we're given a curve that's just made out of r and theta. So that means we likely have to use the fact that x is equal to r cos theta and y is equal to r sine theta. And then using the fact that dy on dx is equal to dy on d theta divided by dx on d theta. And then subbing in theta is equal to pi on 6, we can find the gradient. So how do we do that? Well, we know r is equal to 6 sine 2 theta. And we know y is equal to r sine theta, which we just proved. If r is 6 sine 2 theta, that means I can plug this right into where r is. So we get y is equal to 6 sine 2 theta sine theta. Right? Using a similar method for x, which is r cos theta, we get x is equal to 6 sine 2 theta, which came from here, times by cos theta. Now we have x and y in terms of theta. We know our formula requires dy on d theta and dx on d theta. So we have to find dy on d theta and dx on d theta. Okay, so I see that we have a product of two things, so we should probably use the product rule here. So the derivative of sine 2 theta is 2 cos 2 theta. So multiplying that with 6, you get 12 cos 2 theta sine theta. And now I add that with the derivative of sine theta, which is cos theta. So it's 6 sine 2 theta cos theta. Now I want to find when theta is equal to pi on 6. And this gives something, if you manually plug it in, it should give like 15 on 2, if I believe. Now we're going to do the exact same thing with dx on d theta. So the diff of sine 2 theta is 2 cos 2 theta. So we get 12 cos 2 theta cos theta. But this time, the diff of cos theta is negative sine theta. So it's going to be minus 6 sine 2 theta sine theta. Now we do the exact same thing. We're going to sub theta is equal to pi on 6. And we should get dx on d theta as 3 root 3 on 2. Now remember our formula that dy on dx was the diff of y divided by the diff of x. So I can see that dy on dx is just going to be 15 on 2 divided by 3 root 3 on 2, which is just 15 on 3 root 3, or 5 on root 3. So yeah, that's how we do it. All we did was we just turned x and y in terms of theta alone, such that we can plug it into our dy on dx formula and sub in theta when theta is pi on 6. And that's how we get dy on dx. Are you all good with that? All right, so now let's move on to the first fundamental theorem of calculus. Now it looks pretty complicated, but the way it works, so if f is a continuous function defined at ab, then the function capital F, which is defined by the integral from a to x of f of t dt, which is continuous and differentiable, then we know that capital F, when we diff it, we just get f of x back. So what does that even mean? So we know that integral ax f of t dt just tells us, okay, it's just going to be the area under f of t, or f of x, I should say, from x is equal to a to x essentially. So if I were to draw that, so imagine I just have some function here, and I have a starting point a, and I have some point x, and here we have an area. If I call this capital F of x, what the first fundamental theorem of calculus states that if I find the derivative of the area, or in other words, how the rate of change of area as x changes, it's just going to give me f of x back. That's essentially just what it says. Now, if you guys want just a quick run through on how this works, so imagine let's just draw the same function, f of x. That's the same point a, and we have x. Imagine I just increase the area very slightly by a really small amount. So this x point, I'm going to call it x plus delta x, where delta x is just a really, really small change in x. It's like a really tiny change in area. So if it's really, really small, or we made like a really thin rectangle, right? The height of this is basically just going to be f of x. Because it's really, really thin, so we know that the change in area, which is basically how much extra area we added in, is going to be the width, which is a really, really thin width, multiplied by the height, because it's basically like a really thin rectangle, right? So now I get the change in area, I'll call it the change in area, divided by the change in x is basically f of x. But remember I said capital F of x was the area under f of x from a to x. So that means the change in area is basically the same thing as the change in capital F of x. And that's how you get capital F of x, the diff of it is equal to f of x. That's just kind of like an intuitive way on what the first fundamental theorem of calculus says. Do you understand? All right, so now let's move on to the second theorem. A little bit easier because we could have done this in high school before, but what it says, if f dash of x is just f of x, that means if we have the integral from a to b of f of t, then it's just going to be subbing in the upper bound of the antiderivative minus subbing in the lower bound. So just a quick example, integral 1 to 2, just x dx. If f of x is x, and I know that it has an antiderivative of x squared on 2, that means this is just going to be f of 2 minus f of 1, which is 2 squared on 2 minus 1 squared on 2. Yeah, it's just basically finding the area under the curve from a to b. That is what the second fundamental theorem of calculus states. Are we all good? Yep. So now let's try apply to this question here, which says, okay, find the derivative d of dx for the integral from 0 to the hyperbolic sine of x, which you can pronounce it as sinh of x or shine of x. It's not really agreed upon. I'll just say shine because it's easier to say, of cos t over root 1 plus t squared dt. So this kind of looks similar to our first fundamental theorem of calculus, right? Where we said the derivative of some, let's say some constant, a to x, f of t dt, was just f of x. Now it looks similar, except for the fact that we don't have x, we have a function of x. So that means we've got to change it to a function of x if we want to use the fundamental theorem of calculus. So I'll rewrite it here. So it's from 0 . So if I want to change this to a single variable, there's a really easy way. I'm going to let u, a single variable, equal to the top. So that means I can actually replace this with u later. So that means du on dx. You might be wondering, why are we finding du on dx? Well, you will see we know the derivative of sine is cos. So now what we can do is I can turn this into integral from 0 to not sine of x, but u this time. And the inside stays the same. But remember from our first fundamental theorem of calculus that it had to be d of dx to x, not d of dx to u. So that means this should be not d of dx, but d of du. But our original question had d of dx, so we have to multiply it by du on dx, kind of like the chain rule. So we know that by the first fundamental theorem of calculus, our expression on the left here is just going to be subbing u in, like so. And this is why we found du on dx earlier, which we said was cos of x. But remember, our original derivative was in terms of x, not u. So we have to back sub in. Remember, our original substitution was u equals sine of x. So I have to back sub sine of x where u is. So doing that, we get cos of sine x becomes root 1 plus sine squared x plus x. And from our identities, 1 plus sine squared x is just the same thing as cos squared x. Now if you root that, you get cos x. So we can actually just cancel the top and bottom from just our hyperbolic trig identities. So all we're left with is the cos of sine of x as our final answer. Do you have any questions with any step? All right, so that was a bit bothersome. What the solution gives is a neat little formula that we can follow. So we have a bunch of symbols everywhere. I'll briefly explain how it works. So imagine I have x squared. Let's do something easy, like sine of t. The way we do it, if we're finding this, we take the top, we diff it, and then we multiply by subbing the top in. So it's going to be sine x squared. Then we minus the bottom, we're going to diff it, which is just 1. And then we're going to multiply by subbing the bottom in, which is sine of x. Now using this formula, what we can do is we obtain this cos of sine of x, because remember our original expression was this, and it has sine of x on the top. What we did was we subbed sine of x into t. That's how we have sine of x here, cos of x, and then we minused cos of 0 because we had 0 here. So we subbed 0 into where t was. So minus cos 0 over root 1 plus 0 squared times 0. And we just get cos of sine of x, which is our original answer, same way we got. So this is just a neat little formula, I guess you can use. Are we all good? So now we're going to be looking at this trick called integration by parts. And what integration by parts is, it's just a neat little formula that allows us to integrate the product of two different things. Where did it go? It's okay. That's annoying. Oh, nice. I know what to use for it. Right. Thanks. Hey, how do I zoom? Full screen? Yeah. Okay, thanks. So integration by parts, it's just a formula if we have an integral of two different things together. If you guys want to know where this comes from, I'll just briefly go through it. So we know the product rule. If we diff it, we're going to get the diff of the first term times the second term plus the first term times diff of the second term. And if we just integrate this all in terms of dx, then this cancels out. So you just get uv is equal to integral v du plus integral u dv. And rearranging it, we just get our formula again. But that's not too important. The important part is knowing actually how to use this formula. So I will give an example of how we're going to recognize. So if I have an integral like x times e to the x dx, I see that, okay, it's two things multiplying together. So I should probably use integration by parts. But notice how in the formula we have u and a v, but the question doesn't actually tell us what's u and what's v. So we have to figure out what it is by ourselves. And there's a really easy way to figure out. There is this acronym called LI8. And what it stands for, this stands for log. This stands for inverse trig. This stands for any algebraic related expression. This stands for trig, and this stands for any exponential. And the priority list goes this way into let u equal something. So what does it mean? Let's look at our example here. So we have x times e to the x. I know x is an algebraic term. E to the x is an exponential term. And I see in our acronym, algebraic is higher priority. So that means I should let u equal x. And remember, our formula was u dv. So dv should be e to the x dx. Now the way we do it is we just fill out our table like this. So du is the diff of x, which is 1. V is the integral of dv. So the integral or the antiderivative of e to the x is just e to the x. And now we plug it into the formula uv minus v du. So this becomes uv x times e to the x minus integral v, which was e to the x, du, which was just 1. And I know that the integral of e to the x is just e to the x, so it's just x e to the x minus e to the x. Let's see. This is just generally how we're going to do inverse trig. Not inverse trig, sorry, by parts. So now let's look at this question here. We have to use integration by parts to evaluate the integral from 0 to root 3 of inverse tan of x. It looks like we have a problem because I said earlier, if we want to use by parts, it has to be a product of two different things. However here, we just have inverse tan of x. But actually, we can treat it as a product because it's actually 1 times the inverse tan of x. And looking at our priority list, we said that inverse trig was second, while any algebraic term, like 1, is below it. So we have to let u equal the inverse tan of x and dv equal 1 dx. So filling out the table, I know du is the derivative of inverse tan of x, which is given by this, and v is the integral of 1, which is x. Now I plug that into the formula, which was uv minus integral v du. So plugging it in, you get x inverse tan of x minus integral x over 1 plus x squared dx. But this time, notice how we have bounds. So easiest way, from here, we just chuck our bounds. So root 3, 0, 0, root 3. And then you just solve the integral normally. It may have disappeared again. I think it's just this. Yeah, yes, so weird. Why does that happen? So yeah, using the Liar rule that I mentioned earlier, we view the integral as 1 times inverse tan of x. And because inverse trig is on higher priority, we let u equal inverse tan of x because du is 1 over 1 plus x squared dx. dv in turn becomes 1 dx. So v is x. And then we sub it into our formula where this right here is uv, this is v du. and we plug in our bounds and solving this integral, if you're wondering, x over 1 plus x squared can actually be written as half 2x on 1 plus x squared, such that the diff of the bottom is actually at the top, so it is going to be the natural log of 1 plus x squared. So that's how you integrate that. And since we had bounds, we just plug in the bounds. For example, in here, we're going to plug in root 3. So root 3 tan inverse root 3 minus 0 tan inverse 0. And same thing for the ln, and substituting everything, this is our final answer. So do we kind of get how by parts works? Yeah, it's just a formula. If we have a product, we can chuck it in this formula, but you have to be careful because sometimes if you don't follow this rule, then you can get something even more messy. So if I just go back to the same integral, remember how we let u equal x? If I let u equal e to the x this time, so I'll just follow the same table. This is e to the x dx. dv this time wasn't e to the x, it's now x. So v is now x squared on 2, because the integral of x is x squared on 2. It keeps disappearing on me. Okay. So now from here, if I now plug in the same formula, you get x squared on 2 e to the x minus integral x squared e to the x on 2. Just putting in the same formula, I notice how we got an even more complicated integral. So yeah, that's why we have to follow this priority, because by parts can simplify, but it can also overcomplicate our integral as well. So that's just one thing to be careful of. Are we all good? Now we're going to be looking at the limit test. So before I get into this, I'm going to quickly just refresh. If I have an integral, let's just say a to infinity, f of x dx, and this becomes some finite number, 1, 2, 3, then I can say this integral converges. However, if I have some integral like this, and it doesn't become a finite number, like 1 or 2, then we say this diverges. A visual way you can kind of think about this is, imagine I had f of x that looked like this. So from A, I can see that as x becomes really, really big, this area is probably going to converge to some number. However, if I have g of x that looks something like this area is just going to get bigger and bigger and bigger, and we're not going to actually get a number for this. So that's just basically convergence and divergence. So how do we know if something converges and diverges? So there's this thing called the limit test. So suppose that f and g are integrable functions that are not negative on a to infinity, and that if we take the limit as x approaches infinity of f of x divided by g of x, and it becomes L, where L is some positive number, that means either both f of x and g of x converge, or both have to diverge. So let's try using that here. So we have to determine whether this integral from 1 to infinity of x over root x power 5 plus x cubed plus 1 converges or diverges. Well, just to note, we said it has to be non-negative. Okay, I can't draw. Non-negative on a to infinity. I accidentally moved it, but it's fine. Yeah, so we said it was non-negative on a to infinity. So you have to check if this is non-negative first. Well, I know, okay. So for x is greater than 1, because that's our lower bound. X is positive, x power 5 is positive, x cubed is positive, 1 is positive. Okay, we're all good. This integral is positive. So we can use this limit test. So I'll show you how it works. So I'm going to let f of x be whatever was in that interval. So this right here. But remember, our little limit test here also had g of x. So that means I need to choose a g of x. And the easiest way to choose a g of x is to see how is f going to behave when x becomes really, really big. So I know that when x becomes really, really big, on the denominator here, x cubed and 1 is going to have a really, really small impact on x power 5 because it's a lower power. So I can say that as x becomes really, really big, f of x is just going to tend to x over root x power 5 because the other two terms, they don't really make a meaningful difference. And I know this is x divided by x power 5 on 2, which is x to the negative 3 on 2. Now, this is what I let g of x equal to be. So g of x is going to be x to the negative 3 on 2. I'll explain why we do this. So after we found g of x, we can plug it into our limit test, which was as lim x approaches infinity, f of x and g of x equals the limit as x approaches infinity, x over our original value over x to the negative 3 on 2. And if we simplify this, I'll just look here to save time. What happens is that it becomes 1. So here, I just moved it to the top. That's how we get x power 5 on 2 here. And what we did was we multiplied the top and bottom by 1 over x to the 5 on 2. So the numerator becomes 1. And the denominator here becomes the root of 1 plus 1 over x squared plus 1 over x cubed. And as x becomes really, really big, these fractions are just going to become 0. Hence, our limit tends to 1. So now, since we found that the limit as x approaches infinity, f gx is 1, and 1 is greater than 0, I know that both f of x and g of x, they have to both converge or both diverge. So how do we know that? Well, we chose g of x to be x to the negative 3 on 2. If I take the same integral from 1 to infinity of x to the negative 3 on 2, which looks like this is actually in the form of what we know as the p integral, which looks like this. And we know for a fact that this integral here, when p is greater than 1, so for example, 1 over x squared, 1 over x cubed, it's going to converge. But when p is smaller than or equal to 1, like for example, 1 over x to the power half, it's going to diverge. And notice, this is our g on the top here. And we have x to the power 3 on 2 on the bottom. And 3 on 2 is greater than 1. So we know for a fact this diverges. And remember from our limit, I said both f and g have to both diverge or both converge. Oh, sorry. Since 3 on 2 is greater than 1, it's going to converge because p is greater than 1. And because I said that f and g have to both diverge or both converge, and since we proved g converges, f has to converge as well. So here, as the limit became 1, we know that both f of x and g of x converge or diverge. This is our p integral, and it converges if p is greater than 1. In our example, since the integral from 1 to infinity, g of x, was 1 over x to the power 3 on 2, and we know 3 on 2 is greater than 1, we know this here converges. Thus, f has to converge as well. So that is basically how the limit test works. I know it was a lot. Do you have any questions though? Alright, so let's move on to log and exponentials. So I'm assuming you guys probably have a good understanding of what log and exponentials are. So we know log looks something like this, where it's defined on x is greater than 0, and we know exponentials look something like this. So what I decided to do was give a question that we have to use our knowledge of log and exponentials to solve. So we have a limit here. So as limit, as x approaches 0, from the positive direction, we have to find sine x to the power of tan x. So Oh, it nearly disappeared on me. It disappeared on me. Why does it do that? Yeah, sorry about that. So, as x approaches 0 from the positive side of sine x to power tan x. So if I just try and sub in 0, we get sine 0, which is 0, and tan 0, which is 0. So it becomes in the form 0 to the 0, which is indeterminate. So what we can do instead, so if I let y equal this limit here, I can actually take the log of both sides such that it becomes ln limit x approaches 0 positive sine x on tan x. And a property of limits allows us to just jump the limit to the inside here. So it's limit, not limit, ln sine x to the tan x. And we know from a property of logs that anything on the power jumps to the front. That's so. Are we all good so far with what I did? Yeah, so now if I just try and sub in 0 after doing that manipulation, okay, tan x is 0, that's fine. But here, sine x, when x is 0, is going to be 0. But we can't have ln 0 because I said that ln is defined only when x or when the inside is greater than 0. So we're kind of stuck. Actually, there is another trick we can do. What I can do here is I can actually turn it into a fraction like so. So we know the fact that cot x is 1 over tan x. So tan x should be 1 over cot x. And now we have a fraction. So if I try subbing in x is 0, I know this becomes negative infinity, while the bottom becomes infinity if you look at the graphs. So that means now we can use L'Hopital's rule. So once we use L'Hopital's rule, we get limit as x approaches 0 from the positive direction of cot x over negative cosecant squared x. And then this becomes, we know cot x is cos x over sine x. And I have to divide that by negative 1 over sine squared x, which is cos x over sine x times negative sine squared x. These cancel, so you get negative cos x times sine x. And we know that when x is 0, our entire thing is going to be 0. Hence, we get ln y is 0. So since ln y is 0, we can raise e to the both sides. And we know e to the 0 is 1. Therefore, our original limit y is 1. So that's how we used properties of ln. We logged both sides. We moved the tan to the front. And we were still stuck since ln of 0 right here. When we sub in 0, we get sine of 0, which is 0, which gives us ln of 0, which is undefined. As such, to fix this problem, we changed it into a fraction form. And now since this was in the form infinity over infinity, we can use L'Hopital's rule to get cot x over negative cosecant squared x, which after subbing in 0, x is 0, we get 0. Therefore, ln y is 0, so original limit y has to be 1. Do you have any questions? All right, so now we're going to be looking at hyperbolic functions. So here are just a few definitions on what they are. Hyperbolic cosine, which is cosh, is just given by half e to the x plus e to the negative x. And hyperbolic sine, shine, is defined by half e to the x minus e to the negative x. So if you want to know, it looks kind of like this. This is what cosh x looks like. And shine x looks something like this. But now, you might be wondering, okay, what about the hyperbolic tan? Well, it's very similar to what we already know. It's just going to be shine of x divided by the cosh of x, which is half e to the x minus e to the negative x, which is shine, divided by half e to the x plus e to the negative x. That gives e to the x minus e to the negative x over e to the x plus. That's just what the hyperbolic tan looks like. So those are a few definitions. However, what we're going to do is we're going to see if we can use those hyperbolic trig functions to do an integral like this. So here, evaluate by a hyperbolic substitution, we have the integral of x squared over root x squared minus 1. So I see that, okay, from our hyperbolic trig identities, I know that 1 plus the sine squared of x is cos squared of x. So if I minus 1 from both sides, I get cos squared x minus 1. And if I root both sides, notice how this is pretty similar to the form x squared minus 1. So that tells me that I should probably let, for example, x equal cos of theta here. So that's what we're going to do. We're going to let x equal cos, or okay, this time I let u. So dx on du is the sine of u. So root x squared minus 1 is the sine of u from what I showed earlier. So if we substitute into integral, so we put cos u into here. So we get cos squared of u over sine of u times the sine of u du. And then we get cos squared u left. Now there are a few different ways we can go about this. One way is we're going to use the identity cos squared u equals 1 plus cos 2u over 2. And then we get this. And we can compute the integral because we know that the integral of cos 2u is half sine 2u. And this is what we get. However, remember our original integral. Oh, it just disappeared. Our original integral wasn't in terms of u at all. It was in terms of x. So what we have to do is, since x is equal to cos u, I have to back sub. So u is going to be the inverse cos of x. And using the fact that the sine of 2u is 2 sine u cos u, we get the sine of 2u is 2x times root x squared minus 1. And we back sub these two in. So u is inverse cos of x, we put it back here. Sine of 2u is this, put it into here. And thus we get our final expression as the inverse cos of x divided by 2 plus x root x squared minus 1 divided by 2 plus c. So that is how we can use hyperbolic trig to do integrals like this. So there are other ways because that's just the beauty of integrals. Like for example, I know the fact that 1 plus tan squared theta is sec squared theta, and sec squared theta minus 1 equals tan squared theta. So I can also let x equal sec theta, but the fact that we know this hyperbolic trig identity just opens up new methods to do the same integral. Are we all good? Yep. So that is it. Thank you guys for coming. Yeah, I think we're in the same. On the stream? Yep. And